Everyone knows that steam locomotives push the boundaries of engineering. But what happens when you push so hard that the machine literally destroys itself from the inside out? In the autumn of 1904, a locomotive sat silent in a Pennsylvania workshop, its boiler cracked open like a broken egg. Engineers stood around it, mouths dry, staring at something they'd never seen before. The steel plates that should have been rigid and strong had warped. The stays that held the firebox together had pulled loose, and inside, where white-hot fire should have met water and created steam, they found something that shouldn't exist: solidified metal that had once been liquid. The boiler had melted, not failed, not ruptured, melted. This wasn't supposed to be possible. Boiler steel doesn't melt at operational temperatures. It can't. The margin of safety is enormous, yet here was the evidence, undeniable and terrifying. And the worst part, this was the second time it had happened to the same locomotive. The machine at the center of this disaster was an experimental compound locomotive built by the Baldwin Locomotive Works, designated simply as Test Engine Number 6000. It was never meant for regular service. It was built for one purpose: to discover the absolute limits of steam power. Baldwin wanted to know just how hot, how powerful, how efficient a steam engine could become before physics said no. They found out. The early 1900s marked the peak of steam locomotive development. Engineers across America and Europe were locked in a technological arms race, each trying to extract more power from water and fire. The fundamental equation was brutally simple. Higher pressure meant more power. Higher temperature meant higher pressure. So the quest became about heat, more heat, hotter boilers, hotter fireboxes, hotter steam. Most locomotives of the era operated with boiler pressures around 200 pounds per square inch, and firebox temperatures hovering near 2,000 degrees Fahrenheit. These were proven, safe numbers. Thousands of engines worked within these parameters every day without incident. But Baldwin's engineers believed they were leaving power on the table. If you could push the pressure to 350 psi, maybe 400, and drive the firebox temperature past 2,800 degrees, you could theoretically double the tractive effort without doubling the size or weight of the locomotive. The mathematics were sound. The metallurgy, however, was another question entirely. Test Engine 6000 rolled out of Baldwin's Eddystone Works in March 1904. It was a peculiar-looking machine, squat and heavily reinforced, with a firebox nearly twice the normal thickness. The boiler was built from nickel-steel alloy, the best material available. Extra stays crisscrossed the firebox crown sheet. Water jackets surrounded every high heat surface. The designers had thought of everything. Almost everything. The initial test runs were promising. The engine built steam rapidly, reaching operational pressure in half the time of a conventional locomotive. Engineers noted with satisfaction that at 300 psi, it developed tractive effort comparable to engines nearly 50% larger. The compound expansion system worked flawlessly, extracting every possible joule of energy from the superheated steam. On paper, Test Engine 6000 was a triumph. Then they pushed it harder. The test protocol called for gradually increasing both firing rate and pressure over successive runs. By late April, they were operating at 375 psi, with firebox temperatures estimated at 2,750 degrees Fahrenheit. The locomotive performed magnificently. Crews reported that the engine pulled like nothing they'd ever experienced, accelerating loaded test cars with startling ease. Steam consumption was remarkably efficient. Baldwin's engineers began drafting plans for a production series. On May 3rd, during a maximum effort test run, the fireman noticed something wrong. The water level in the sight glass was dropping faster than it should, even accounting for the high steam demand. He called out to the engineer, who immediately shut the throttle and applied the brake. As the locomotive coasted to a stop, a thin stream of water began dripping from beneath the boiler, hissing as it struck the hot running board. They'd sprung a leak, not unusual, not particularly alarming. Leaks happened, but when they opened the firebox door to bank the fire, they saw something that made their blood run cold. The crown sheet, the steel plate that forms the top of the firebox, was glowing. Not the normal cherry red of hot metal under fire, but a brilliant yellow-white, the color of metal approaching its melting point. And it was sagging, visibly sagging, bowing downward under its own weight despite the stays that should have held it rigid. They dumped the fire immediately, flooding the firebox with cold water, despite the risk of thermal shock cracking the boiler. Steam exploded from every seam and rivet as the temperature differential sent shock waves through the metal. It took 6 hours for the boiler to cool enough to safely inspect. What they found was worse than a simple leak. 3 of the crown sheet stays had pulled completely through the steel, leaving ragged holes. The steel around each failure point had deformed plastically, stretched and thinned like taffy. Sections of the firebox showed evidence of incipient melting, with the crystalline structure of the steel altered in ways that suggested it had approached within 100 degrees of its liquidus temperature. Baldwin's metallurgists were called in. They examined the failed components under microscopes, tested the material composition, calculated heat transfer rates. Their conclusion was unequivocal. The firebox had been operating at temperatures that exceeded the design limits of the steel by a substantial margin. The localized heating around the crown sheet, combined with the extreme pressure differential, had created conditions where the metal temporarily lost its structural integrity. In layman's terms, they'd gotten it so hot that it started to melt. The locomotive was rebuilt with an even stronger boiler, using a newly developed chrome-molybdenum steel alloy that promised better high-temperature strength. Additional water circulation was engineered into the firebox design. More stays were added. The crown sheet was made thicker. Every calculation was checked and rechecked. Test engine 6000 returned to service in July. The engineers were more cautious this time. They established strict protocols: never exceed 350 psi, carefully monitor firebox temperature, maintain constant water feed. For 2 months, the locomotive performed flawlessly. The modifications seemed to have solved the problem. Confidence grew. Maybe they really had found a way to break through the thermal barrier. In September, Baldwin's chief engineer authorized a final test series. They wanted to know the true maximum. Not the safe maximum, not the recommended maximum, but the absolute physical limit. Where would the machine finally say no? They found out on September 27, 1904. The test began at dawn. Pressure built steadily. 300 psi, 325, 350. The fireman was feeding coal at a furious rate, maintaining a white-hot bed of flame. Temperature measurements from thermocouples embedded in the firebox wall showed readings climbing past 2,900 degrees. At 375 psi, the The locomotive was developing nearly 80,000 pounds of tractive effort, a staggering number for an engine of its size. The engineer radioed back to the observers. "She's pulling like the devil himself, no signs of distress." They pushed to 390 psi. At 11:42 a.m., one of the trackside observers noticed something peculiar. The locomotive's exhaust steam, normally invisible except as a heat shimmer, had taken on a faint reddish tinge. He mentioned it to his colleague, who dismissed it as a trick of the light. At 11:44 a.m., the water level in the boiler dropped precipitously. The low water alarm began to shriek. The fireman immediately stopped firing. The engineer shut the throttle and began coasting, letting the locomotive's momentum carry it while steam pressure stabilized. At 11:46 a.m., the crown sheet failed catastrophically. The sound was unlike any boiler explosion the witnesses had ever heard. Instead of the sharp, percussive bang of a pressure vessel bursting, it was a deep, tearing groan, like metal being ripped apart. Steam didn't explode outward. It boiled upward through the widening crack in the crown sheet, filling the boiler with a churning mass of water and vapor. The automatic pressure relief valves opened, venting steam in a screaming rush, but the damage was done. When the locomotive finally ground to a halt 300 yards down the track, water was pouring from a 2-foot split in the crown sheet. The post-failure inspection revealed something unprecedented. The crown sheet hadn't just cracked. Portions of it had partially melted and re-solidified. Microscopic examination showed dendritic crystal structures, characteristic of steel that had been molten and then rapidly cooled. The stays hadn't pulled through this time. They'd melted off, the steel simply liquefying under conditions that should have been impossible in a steam locomotive firebox. The thermocouples told the story. In the final minutes before failure, localized temperatures in the crown sheet had reached 2,870 degrees Fahrenheit. The melting point of the chrome molybdenum steel used in the boiler was 2,150 degrees. For a brief period, small pockets of the firebox crown had literally turned to liquid while the locomotive was in operation. Baldwin quietly shelved Test Engine 6000. The rebuilt locomotive sat in storage for 2 years before being cut up for scrap. No official report was ever published. The experiment was too embarrassing, too dangerous, too far beyond acceptable risk. But the data survived. Locked away in Baldwin's technical archives, the test results from Engine 6000 became a cautionary tale passed among locomotive designers. The numbers were clear. Steam locomotives had reached their thermal limit. You could not simply keep adding pressure and temperature indefinitely. Physics would push back, and physics always won. The irony is that Engine 6000 had actually succeeded in its mission. It had discovered the absolute boundary of steam technology using early 20th century materials. That boundary was approximately 375 psi and 2,700 degrees Fahrenheit in the firebox. Beyond that threshold, you weren't building a locomotive anymore. You were building a furnace that occasionally moved. Other manufacturers learned the lesson without having to melt their own boilers. By 1910, the industry had settled on an upper limit of 300 psi for superheat designs, with firebox temperatures carefully controlled below 2,500 degrees. These became the standard parameters for high-performance steam locomotives for the next 4 decades. A few experimental engines pushed slightly beyond. The Pennsylvania Railroad's S1 duplex hit 310 psi, The Norfolk and Western's J-class reached 315 psi, but no one ever approached the extremes that destroyed Engine 6000. The quest for more power shifted direction. Instead of hotter steam, engineers focused on better steam, distribution, more efficient valve timing, improved drafting, and compound expansion systems. The gains were incremental but safe. Locomotives got larger, not hotter. By the time diesel-electric locomotives began displacing steam in the 1940s, the thermal efficiency of the best reciprocating steam engines had improved by nearly 40% compared to 1904, without anyone melting another boiler. Test Engine 6000 exists now only in fragmented records, a few photographs, some test data sheets, and cautionary notes in engineering manuals. The locomotive that melted its own boiler twice never hauled a single revenue train, never pulled a passenger car, never earned $1 for Baldwin. It was built purely to find a limit, and it found that limit by destroying itself. There's a brutal honesty in that. We often celebrate engineering triumphs, the machines that pushed boundaries successfully. But perhaps there's equal value in remembering the machines that pushed too far, the experiments that failed so spectacularly that they redefined what too far actually meant. Engine 6000 didn't just fail. It failed in a way that was quantifiable, repeatable, and ultimately instructive. It gave the industry a precise number, 2,750 degrees Fahrenheit. Beyond that, steel stops being structural. It becomes something else, something fluid and treacherous. Every locomotive built after 1904 inherited that knowledge, even if the engineers who designed them never knew the story. The specifications they followed, the safety margins they respected, the materials they selected, all of it traced back, in part, to a machine that got so hot it melted itself from the inside out. Twice. Some boundaries are theoretical, some are practical, and some are written in solidified steel, dripping from a crown sheet that never should have turned liquid. Baldwin's engineers had asked, how far can we push steam power? Test Engine 6000 answered, this far, and not 1 degree more.